All right, we're going to look at converting between fractional exponents, such as a fraction of m over n, and radical forms, such as the nth root of b to the power of m. And b just represents some base that we're raising to the power of m over n. We're taking the nth root of b and raising it to the power of m. And that's our general form. And we sort of have to assume for now that b is positive. Because when b is negative, it can create some issues. So right now, everything we're saying is just assuming that b is positive. We might as well assume m and n are also positive. So if we want to see what this might look like with an example, we can consider 4 to the power of 3 halves. And so, well, what does this mean? If we consider repeated multiplication by 4, we start with 1, then 4, 16, and 64. And each of those represents a multiplication by 4, times 4, times 4, times 4, which is what our exponents represent. And this represents 0 multiplications by 4, 1 multiplication by 4, 2 by 4, and 3 multiplications of 4. And so if we want to raise 4 to the power of 3 halves, well, that's like 4 to the 1.5. So we might be interested to think, oh, well, what's halfway between multiplying by 4 one time and multiplying by 4 twice? And so we need to subdivide a multiplication of 4 into 2 steps. And that turns out is multiplying by the square root of 4. And the square root of 4 we know is 2. So we can also think about that as multiplying by 2. Now 4 times 2 is just going to get us to 8. And so the 4 raised to the 3 halves power, or 4 raised to the 1.5, is equal to 8. Or halfway between 4 and 16, thinking about multiplications by 4 is 8. But when we look back to our power or our fractional power and want to represent it as a root, we could have also written this as the second root, or the square root of 4 raised to the 3rd power. And if we want to think about it this way, we can think about of all our subdivisions of multiplying by square root of 4, square root of 4 again, and we do it 1, 2, 3 times. So we have square root of 4 multiplying by square root of 4 3 times to get us from no multiplications to 1.5 multiplications of 4, or 3 multiplications of square root 4. And that's going to give us 8. And the square root of 4 we know to be 2, and 2 to the 3rd power is 2 times 2 times 2 does equal 8. Just square root 4 times square root 4 times square root 4. So this is the main idea behind fractional exponents and turning them into radical form. So let's look at another example here. Let's consider a different number, 3 to the 3 halves power. And so we can think of this as 3 to the 1.5, or we can think of it using radical notation, the square root of 3 raised to the 3rd power. And so if we break this down into multiplications of 3, we start at 1, then go to 3, then 9, then 27. And each one of these represents a multiplication of 3, and times 3 again. But we're interested in, well, we have 0, 1, 2, 3. And we want to know, well, what's between 1 and 2? What's 3 halves here? So we want to raise 3 to the 1.5. And rather than going the full square root 3 here, we're now breaking that into 2 steps. So we go part of the way, halfway, and then halfway again. And so that represents multiplying by square root 3 and by square root 3. And unlike the square root of 4, the square root of 3 is not a whole number. So the best we can do is express this simply as 3 times the square root of 3. Or we could try to get to a decimal approximation. So we get 3 square root 3. So this actually turns out to be equal to 3 square root 3 as well. If we break down every single step into square roots of 3, we have a multiplication of square root 3, a multiplication of square root 3, and we have 1, 2, 3 multiplications of square root 3. But remember, that is the power. That's not what this 3 out in front is. Square root of 3 cubed is 3 multiplications of square root 3, right? Square root 3 times square root 3 times square root 3. It just so happens that when we multiply two square roots by each other, well, the square root of 3 times the square root of 3 is just 3, and then we're left with 3 square root 3. So that's more of a coincidence that we had 3 multiplications and the 3 came out in front. Okay, let's take another example. So let's clear this. And let's look at the example of, let's consider 5 to the power of 3/4. So if we consider repeated multiplications of 5, we could start at 1, which is 0 multiplications of 5, then go to 5, then 25, then 125, and so on. And so we can multiply by 5, and by 5 again. But this denominator of 4 is saying we want to break up these stages rather than going from 0 multiplications to 1 multiplication to 2 to 3. We want to break each of those into stages of 4. So we actually are interested in figuring out, well, what's 1/4 of the way there? What's 2/4? What's 3/4? 1 gets us to 4/4. Then we get to 5/4, 6/4, 7/4. So we can think about breaking up our multiplications a little bit more. And so 1/4 of the way to a multiplication of 5 is given by the 4th root of 5. And if we want to do that 3 times, we need to raise it to the 3rd power. Because if we want to take 5 to the 3/4, if we want to end up right here, we need to multiply by the 4th root of 5, and then multiply again by the 4th root of 5, and then multiply again by the 4th root of 5. And that's going to get us to 5 to the 3/4 power. And so we would end up with the 4th root of 5 cubed, which is the conversion of our notation. We take our numerator of the fraction, and that becomes our power. We take the denominator of our fraction, and that becomes our root. And that's how we can convert forms. And this is sort of the why behind what's happening there. And the 4th root of 5 to the 3rd, there's really nothing else we could do other than try to simplify it as a decimal. Alrighty, let's take a look at one more example here. Let's use 5 as a base again. And so we're going to say, this time we'll try 5 to the power of 9/4. And so 9/4 is interesting because this is equivalent to 5 to the 2 1/4, which we know would be equivalent to 5 squared times 5 to the 1/4, or 5 squared times the 4th root of 5. So that's one thing to consider. But if we just go directly to our radical notation, this is also equivalent to the 4th root of 5 to the 9th power. So all of these are valid ways of writing the same thing. And so let's think about, what does it even mean? So if we think about multiplications of 5, we go from 1 to 5 to 25 to 125, with those representing our integer multiplications of 5. 0 multiplications 1, 2, 3. Times 5, times 5, times 5. But we're going to break those multiplications down into fourths this time. So we're going to say 1/4, and then I'll do 2/4, which is a half, 3/4, 5/4, 6/4, 7/4, 8/4, 9/4, 10/4, 11/4. So if I want to consider each of these stages of multiplication, well, this is times the 4th root of 5. And then we got to multiply times the 4th root of 5. And again, times the 4th root of 5. We do it 3 times. And then 4 times gets us to 5. Because, right, 4th root of 5 is defined as the thing that we multiply by itself 4 times to get to 5. Or said differently, 4th root of 5 to the 4th equals 5. But we could keep using this subdivision and keep going and do it 1, 2, 3, 4 more times, and then again. So altogether we have 1, 2, 3, 4, 5, 6, 7, 8, 9 multiplications of the 4th root of 5. So I could write that out, and we'll end up right here. And that would be, if it's 9 multiplications of the 4th root of 5, we have the 4th root of 5 to the 9th power, right? So that's what we would have to do to get there. And if we write this out, we can say 4th root of 5 times the 4th root of 5 times the 4th root of 5. There's 3, 4, 5, 6, running out of space. Pull this over. Times the 4th root of 5. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Equals the 4th root of 5 to the 9th power, right? But the other thing we could do is we can kind of simplify here. Because we said every time we multiply by the 4th root of 5 times, well, that's just 5. So 1, 2, 3, 4 here, that just equals 5. And then 1, 2, 3, 4 here, that just equals 5. And then we're left with a single multiplication of the 4th root of 5. So we can do another 4th root of 5, and that still is equivalent to the 4th root of 5 to the 9th power. And if we wanted to combine our coefficients of 5, we could call this 25 4th roots of 5. It's equivalent to the 4th root of 5 to the 9th is equivalent to 5 to the 9/4, and so on and so forth. Or we could write that as 5 to the 2 1/4, which is equal to 5 squared times 5 to the 1/4. Zoot. Which is equal to 25 times 5 to the 1/4, which is equal to 25 times the 4th root of 5. So it all comes together really nicely, but it's great to have this understanding. Like, yes, we have this rule here. Like, this is just a rule we can use as a shortcut, but it's really, really nice to try to think and develop the understanding, like, well, where is this rule coming from? What does that have to do with repeated multiplication? What does it have to do with getting from one place to the next by multiplying by 5, or by multiplying by a 4th root of 5, or a square root of a number, or a cube root? So hopefully this video was really helpful in trying to explain not only what does a fractional exponent look like as a radical, but why.